Assalamu alaikum wa rahmatullahi wa barakatuh. This is the lecture on the transport of respiratory gases in the respiratory physiology section in the respiratory block. As we mentioned in the previous lecture, that in man respiration involves a series of integrated processes or steps in order to provide the cells of the body with oxygen and to remove carbon dioxide from the body. In the previous lecture, we discussed the process of exchange of oxygen and carbon dioxide, and in this lecture we will describe how oxygen is transported in the blood to reach the metabolizing tissues, and how carbon dioxide is transported back to the right atrium, then right ventricle, and back to the lungs in order to be eliminated from the body during the process of expiration. Oxygen is transported in the blood in two main forms. Oxygen which is dissolved in the plasma, and oxygen which is bound to hemoglobin. Most of the oxygen is transported bound to hemoglobin, as we are going to see in the subsequent slides. Carbon dioxide is transported in three different ways. We have carbon dioxide dissolved in the plasma, carbon dioxide bound to hemoglobin, and most of the carbon dioxide is transported in the form of bicarbonate, as we will see in the subsequent slides. Now, before going into the detailed description of the transport of oxygen and transport of carbon dioxide, let's very briefly describe an important law regarding the concentration of gases in a liquid, which is Henry's law. The Henry's law states that the concentration of free gas in a liquid when the temperature is constant is proportional to the partial pressure of the free gas in equilibrium with that liquid. So the concentration of the gas is directly proportional to the partial pressure of the gas. If we are to remove the proportional sign, we need to multiply into a constant, which is the solubility coefficient of the gas. So the concentration of the gas in a liquid equals the partial pressure of that particular gas in the liquid multiplied by its solubility coefficient. You know that most of the plasma is water, so when we say water or plasma in the blood, we mean the same thing. The solubility coefficient of oxygen in plasma or in water is equivalent to 0.003 milliliters of oxygen in each 100 milliliters of the blood per millimeter of mercury partial pressure of oxygen. That of carbon dioxide is 0.07 milliliters of carbon dioxide in each 100 milliliters of the blood per each millimeter of mercury partial pressure of carbon dioxide. So if we divide these solubility coefficients, if we divide the solubility coefficient of carbon dioxide by the solubility coefficient of water, it gives us an indication that carbon dioxide is nearly 25 times more soluble than oxygen in the blood. And it is very important to note that it is the gas which is dissolved in the water on the plasma which exerts the partial pressure of the gas in the plasma or in the blood. So Now we will describe the transport of oxygen in more details. And we mentioned earlier that oxygen is transported in two forms: dissolved in the plasma and bound to hemoglobin. Less than 2% of oxygen is transported dissolved in the plasma, because in the previous slide we mentioned that the oxygen has low solubility in the water or in the plasma. And using Henry's law, we can reach to a conclusion that the oxygen which is dissolved in the plasma is not sufficient to maintain the tissues of the body. It's not sufficient to supply the tissues of the body with the oxygen requirements. So Henry's law states that the concentration of oxygen is equivalent to the partial pressure of oxygen multiplied by its solubility coefficient. Now, oxygen delivery, how much oxygen is delivered to the tissues, is equal to the product of the concentration multiplied by the cardiac output. Remember, the cardiac output at rest is 5 liters per minute. 5 liters of blood go through the tissues at rest. So how much soluble oxygen is present in these 5 liters of the blood? So the oxygen delivery again is equal to the concentration of oxygen multiplied by the cardiac output. And the concentration itself is equal to the partial pressure of oxygen in the arterial blood multiplied by the solubility coefficient. So here we have the amount of oxygen delivered to the tissues in the form of oxygen dissolved in the plasma in each minute. 0.003, this is the solubility coefficient for oxygen, multiplied by 95, which is the partial pressure of oxygen in the arterial blood, multiplied by 5 milliliters of blood per minute, which is the cardiac output. This gives us 15 milliliters of oxygen are delivered to the tissues in the form of oxygen dissolved in the plasma every minute. Remember, the resting oxygen consumption, or the minimum needs of the tissues of the body for oxygen, is 250 milliliters per minute. Of these 250 milliliters of oxygen, only 15 milliliters are transported in the form of oxygen dissolved in the plasma. So this indicates that most of the oxygen is transported bound to hemoglobin. So in fact, greater than 98% of the oxygen is transported bound to hemoglobin. Each molecule of hemoglobin, as you know, is composed of 4 polypeptide chains. We have 2 alpha chains and 2 beta chains in adult hemoglobin, and in each polypeptide chain there is a heme pocket. So each hemoglobin molecule has the ability to bind up to 4 oxygen molecules. And in the heme moiety of hemoglobin, we have iron in the ferrous state. And when each molecule of hemoglobin has 4 molecules of oxygen bound to it, the hemoglobin molecule is fully saturated. So here we have an important physiological concept, which is oxygen saturation. Oxygen saturation is the percentage of the hemoglobin molecules which are fully saturated with oxygen. In other words, each molecule of hemoglobin binds 4 molecules of oxygen. The oxygen saturation of the arterial blood is measured with the pulse oximeter, and I believe you must have seen this in the hospitals and in the healthcare centers. And the normal values of the oxygen saturation of the arterial blood are between 95% and 100%. It means that in the arterial blood, where the partial pressure of oxygen is 95 millimeters of mercury, 95 to 100% of the hemoglobin molecules carry 4 molecules of oxygen. So, the oxygen saturation, again, is the percentage of the hemoglobin molecules which are fully saturated with oxygen. The oxygen carrying capacity, or we call it the oxygen capacity, this is the greatest amount of oxygen. This is the greatest amount, or the biggest amount of oxygen in milliliters that can be carried by the hemoglobin molecules in 100 milliliters of the blood. This is when all the hemoglobin molecules are fully saturated with oxygen. The oxygen content, on the other hand, is the actual amount of oxygen which is carried bound to hemoglobin in 100 milliliters of the blood. So there is difference between the oxygen carrying capacity and the content. For example, in this room where you sit, there are 100 chairs. So the capacity of this room is 100 persons. It can accommodate up to 100 persons. But what actually present in this room is your number. For example, 80 students are present in this room. So the content of the room is 80. And the capacity is 100. So, what is the percentage saturation of the room? It will be the content divided by the capacity multiplied by the 100. And when there are 100 students sitting in the room, in this case the content is equal to the capacity. And this is what we have in the arterial blood. In the arterial blood, when all the hemoglobin molecules are fully saturated with oxygen, the oxygen content is equivalent to the oxygen carrying capacity. So, what is the oxygen carrying capacity? Again, this is the greatest amount of oxygen in milliliters that can be carried in the blood. How much? How many milliliters of oxygen are carried in 100 milliliters of the blood when all the hemoglobin molecules in these 100 milliliters of blood are fully saturated with oxygen? So when each gram of hemoglobin is fully saturated with oxygen, it carries about 1.36 milliliters of oxygen. And you know that the normal hemoglobin concentration of the blood is 15 grams of hemoglobin in each 100 milliliters of the blood. So it is very simple now to calculate the oxygen carrying capacity of the blood. So each gram of hemoglobin in these 100 milliliters of the blood, when fully saturated with oxygen, carries 1.36 milliliters of oxygen. So the oxygen carrying capacity is equal to this number multiplied by 15, so approximately 20 milliliters of oxygen in each 100 milliliters of the blood. This is the maximum capacity, or the oxygen carrying capacity. What about the content? The content is equal to what? The content is equal to the oxygen carrying capacity multiplied by the saturation. Remember, the percentage saturation is equal to the content divided by the capacity multiplied by 100. So when the oxygen saturation is 100%, like what we have in the arterial blood, where the partial pressure of oxygen is 95 milliliters of mercury, the oxygen content is equal to the capacity. When the saturation is less than 100, the content is less than the capacity. Now, let's calculate the oxygen content in the arterial blood. This is the blood which flows to the tissues, and the oxygen content of the venous blood. This is the blood which leaves the tissues. And remember, from the previous slide, we mentioned that oxygen content is equal to the oxygen carrying capacity multiplied by the saturation of oxygen. In the arterial blood, the partial pressure of oxygen is 95 millimeters of mercury. And at this partial pressure of oxygen, the oxygen saturation is 100%. So the oxygen content is equal to the capacity, which is 20, multiplied by 100%, which is 100 by 100. So the content is equal to 20 milliliters of oxygen in each 100 milliliters of the blood. In other words, the content in the arterial blood is equal to the maximum capacity. In the venous blood, the partial pressure of oxygen is 40 millimeters of mercury. And the oxygen saturation is not 100%. It is 75%, as we will see in the subsequent slides. So now the content is 20 milliliters of oxygen multiplied by 75% divided by 100. So it is 15 milliliters of oxygen in each 100 milliliters of blood. In other words, in each 100 milliliters of oxygenated blood flying through the tissues, we have 20 milliliters of oxygen. And in each 100 venous blood leaving the tissues, we have 15 milliliters of oxygen. So from each 100 milliliters of blood flying through the tissues extract only 5 milliliters of oxygen at rest. In other words, the oxygen extraction is 25%. 25%, how did we calculate this oxygen extraction? Because only 5 milliliters of oxygen were taken from the 20 milliliters of oxygen. So the tissues have extracted only 25% of the oxygen which is present in the blood that flows through the systemic capillaries. Now, let's describe another very important concept related to oxygen transport. Remember, we mentioned in the previous slides that the oxygen delivery to the tissues is equal to the product of the oxygen concentration multiplied by the cardiac output. The oxygen content is the oxygen concentration, because we mentioned that the content is how many milliliters of oxygen we have in 100 milliliters of the blood. So this is the oxygen concentration. So oxygen delivery in the arterial blood is the oxygen content of the arterial blood multiplied by the cardiac output. So the oxygen content of the arterial blood is 20 milliliters of oxygen each 100 milliliters of the blood, and the cardiac output is 5,000 milliliters of the blood each minute, which is the 5 liters. So we have 1,000 milliliter of oxygen per minute can be delivered to the tissues. But the tissues do not need all these 1,000 milliliters of oxygen. The tissues, remember, they extract only 25%. 25% يعني ربع الكمية، يعني ربع 1000 ملليلتر of oxygen. ربع 1000 كام؟ اللي هم 250 milliliters of oxygen. So this is the resting oxygen consumption. Okay, so again, it is important to recall that only 25% of the oxygen delivered by hemoglobin in the arterial blood is extracted from the blood as it flows through the tissues. So it is 250 milliliters per minute, and this is the resting oxygen consumption. Of course, during exercise, the oxygen consumption increases. Now, let's describe a very important physiological concept related to oxygen transport, which is the oxygen hemoglobin binding curve. This curve is a graphic illustration of the percentage saturation of hemoglobin with oxygen on the y-axis at different values of the partial pressure of oxygen. So on the x-axis we have the partial pressure of oxygen, and on the y-axis we have the percentage saturation of hemoglobin with oxygen, or we might have the oxygen content, if you like, on the y-axis. So as the partial pressure of oxygen increases, the percentage saturation of hemoglobin with oxygen increases. So we have now this curve, and you can see from the diagram that the curve is not linear, rather it is a sigmoidal curve. Why is it sigmoidal curve? This is due to the positive cooperativity of binding of oxygen to hemoglobin. As one molecule of oxygen binds to the hemoglobin molecule, the affinity of oxygen of the preceding subunits increases. And as the partial pressure of oxygen increases, the oxygen bound to hemoglobin increases. So the percentage saturation of hemoglobin with oxygen, or we call it the oxygen saturation, is dependent on the partial pressure of oxygen. So at a partial pressure of oxygen which is 100, and this, remember, where in the body we have a partial pressure of oxygen of 100? This is the partial pressure of oxygen in the arterial blood. The oxygen saturation is, we take a perpendicular line, then we take a horizontal line. The oxygen saturation is what? Is 100%. So all the hemoglobin molecules are saturated with oxygen. And when the oxygen saturation is 100%, the oxygen content is 20 milliliters of oxygen in each 100 milliliters of blood, or in each deciliter of blood. 1 deciliter of blood is equivalent to 100 milliliters of blood. At a partial pressure of 40, at a partial pressure of oxygen is 40, where in the body we have a partial pressure of oxygen 40, this is the pressure which we have in the venous blood. The percentage saturation of hemoglobin of oxygen is approximately 75%. And at this 75% saturation, the content is 15 milliliters of oxygen in each 100 milliliters of the blood. And this is we mentioned in the previous slides. Again, this is the same thing. This is the curve. And this curve shows the resting oxygen consumption. So this is the oxygen content of the arterial blood. In each 100 milliliters of the arterial blood, we have 20 milliliters of oxygen. This is the oxygen content of the venous blood, 15. So the tissues have taken 5 milliliters of oxygen from each 100 milliliters of the blood. So from 1 liter of the blood, the tissues would have taken 50 milliliters of oxygen. So from 5 liters of the blood, which is the cardiac output, the tissues of the body would have taken 50 multiplied by 5, 250 milliliters of oxygen. which is the resting oxygen consumption. Now, let me ask you a very important question. Do you think, is it the oxygen content or the oxygen saturation which keeps us alive? So in this diagram we have three conditions. We have here a subject where the hemoglobin concentration is 15 grams in each 100 milliliters of blood, which is normal. And we have an anemic subject where the hemoglobin concentration is 10 grams in each 100 milliliters of the blood. And we have here a polycythemic guy where the hemoglobin concentration is 20 grams in each 100 milliliters of the blood. In all these subjects, the oxygen saturation at a partial pressure of oxygen of 100 is 100%. But the content varies. Why? Remember, the content, the oxygen content is equal to what? Is equal to what? The content. The content is how many milliliters of oxygen in 100 milliliters of the blood. Since the anemic guy has less hemoglobin, so his or her oxygen content would be less even when all the hemoglobin molecules are fully saturated with oxygen, because he has less hemoglobin. Okay, so it is the oxygen content rather than the partial pressure of oxygen or the oxygen saturation which keeps us alive. Now, let's describe the oxygen hemoglobin binding affinity. How can we measure the affinity of hemoglobin to bind oxygen? This is measured by what is known as P50. P50, this is the partial pressure of oxygen at which 50% of hemoglobin is bound with oxygen, i.e. 50% of hemoglobin is saturated with oxygen. So this is 50% saturation, so this is P50. P50 is here, is something like 25 or 26 millimeters of mercury. If P50 decreases, see here, so here what happens? The affinity of hemoglobin to bind oxygen increases. If P50 increases, the affinity of hemoglobin for oxygen decreases. And when the affinity increases because of a decrease in the P50, if we plot the curve, this curve now with an increased affinity would be shifted to the left of the original curve. And if the affinity decreases because of an increase in P50, and if we now plot the curve, the curve now would be shifted to the right of the original curve. So, shifting of the oxygen hemoglobin association curve to the left indicates an increased oxygen hemoglobin binding affinity as a result of a decrease in P50. This is the left shift. On the other hand, a right shift of the curve, this is the one in violet, indicates a decreased oxygen binding affinity as a result of an increased P50. So this is the normal position in blue. The left shift with increased affinity is green, and the right shift with decreased affinity is violet. So where in the body you think we have left shifting of the curve? it should be at the level of the lung, because at the level of the lung we need to have an increased affinity of hemoglobin to oxygen. Where in the body we have right shifting of the curve, this should be at the level of the tissues, because at the level of the tissues we need to have a decreased oxygen hemoglobin binding affinity so that oxygen is delivered to the tissues. Oxygen leaves hemoglobin and goes to the tissues. Okay, this is what you mentioned, the same thing as we mentioned in the previous slide. So what are the factors which decrease the affinity of hemoglobin for oxygen and thus increase P50 and cause shifting of the curve to the right? These factors are a decrease in the pH, an increase in the partial pressure of carbon dioxide, an increase in the temperature, and biphosphoglycerate. All these factors are present at the level of the tissues. Another factor which decreases the affinity of hemoglobin for oxygen is hemoglobin S. We'll talk about this in the subsequent slides. What are the factors which increase the affinity of hemoglobin for oxygen and thus decrease P50 and cause left shifting of the oxygen hemoglobin binding curve, an increase in the pH, decrease in the partial pressure of carbon dioxide, decrease in the temperature, and all these factors are present at the level of the lung. Another thing is hemoglobin F. This is the fetal hemoglobin. This is the hemoglobin which is present in the fetus. Remember, the fetus gets his oxygen from the mother, from the hemoglobin of the mother. So the hemoglobin of the fetus should have higher affinity for oxygen to get oxygen from the hemoglobin of the mother. Another cause for the increased affinity of hemoglobin for oxygen is methemoglobin, and when we have carbon monoxide poisoning. So let's talk about now the right shift, then we'll speak about the left shift. So one of the factors which cause shifting of the curve to the right is 2,3-biphosphoglycerate or 2,3-diphosphoglycerate. This is a substance which is produced in the red blood cells as a result of glycolysis, and it is produced in larger amounts when the partial pressure of oxygen is low. For example, at the body tissues, or when there is anemia, or when there is emphysema. Emphysema, this is a disease of the lung, or when there is someone lives at high altitude. So how does 2,3-biphosphoglycerate decreases the affinity of hemoglobin to oxygen and thus causes right shift of the curve? The 2,3-biphosphoglycerate binds to the beta subunits of hemoglobin, and this decreases the affinity of hemoglobin for oxygen. So at the level of the tissues, since we have more 2,3-biphosphoglycerate, we have more oxygen released to the tissues. We mentioned that the hemoglobin S, or sickle cell hemoglobin, results in right shifting of the curve. In sickle cell anemia, or in sickle cell hemoglobin, we have abnormal beta subunits in the hemoglobin, and these abnormal beta subunits in the hemoglobin S, they have decreased affinity for oxygen. Patients with hemoglobin S, if they are exposed to hypoxic conditions or acidosis, these conditions can cause the hemoglobin S molecules to polymerize, and this further decreases the affinity of hemoglobin for oxygen and can cause elongation of the red blood cells, and the red blood cells look like sickles. And the red blood cells can accumulate together and can result in vaso-occlusive crisis because of the occlusion of the small blood vessels. Anyway, I believe you must have covered this condition in the hematology block. Now, the left shift of the curve, this is where in the body we have it at the level of the lungs, because now hemoglobin has got higher affinity for oxygen. And remember, at the level of the lungs, we have a decrease in the partial pressure of carbon dioxide or an increase in the pH. And these two factors, they increase the affinity of hemoglobin for oxygen. And this is what is known as Bohr effect. So, at the lungs, we have an increased affinity of hemoglobin for oxygen. So, hemoglobin needs to pick up more oxygen. So, the affinity of hemoglobin needs to increase. And what increases the affinity of hemoglobin to oxygen is the decrease in the partial pressure of carbon dioxide or the increase in the pH according to the Bohr effect. The decrease in the temperature, which we have again at the level of the lungs, increases binding. So, when the metabolism is increased at the level of the tissues, this decreases the binding affinity of hemoglobin with oxygen, and the curve is shifted to the right, not to the left. So, oxygen is delivered to the tissues. So, another factor which causes left shifting of the curve is what we mentioned, the fetal hemoglobin. Remember, the fetal hemoglobin is not 2 alpha to beta. It is 2 alpha to gamma. So the gamma subunits replace the beta subunits. And because the gamma subunits replace the beta subunits, now hemoglobin has got a greater affinity for oxygen. And the 2,3-biphosphogylacerate has little effect on the fetal hemoglobin because there are no beta subunits. Okay, so now if we plot the two curves, the maternal hemoglobin and the fetal hemoglobin, we would find that the fetal hemoglobin curve is shifted to the left of the maternal hemoglobin curve. Another thing which causes left shifting of the oxygen hemoglobin association curve is methemoglobin. What is methemoglobin? Methemoglobin is the hemoglobin with heme moieties in the ferric state rather than the normal ferrous state. And the hemoglobin moieties in the ferric state, they cannot bind oxygen. So this causes the other heme moieties where iron is in the ferrous state to bind oxygen very, very tightly. So this causes shifting of the curve to the left. What are the causes of methemoglobin or methemoglobinemia? It's caused by nitrates, sulfonamides. Sulfonamides, these are drugs which are used to treat bacterial infection. We have arsenic or deficiency of the enzyme methemoglobin reductase. In normal conditions, methemoglobin is present in very, very small fraction, less than 1% of the hemoglobin. The clinical picture of the methemoglobinemia is skin discoloration when the percentage of methemoglobin is greater than 10%, headache when the percentage is more than 20%, coma when it is higher than 50%, and if the percentage of methemoglobin is greater than 70% of all hemoglobin, the subject would die. How would we treat this? The methemoglobinemia, we treat it with methylene blue. Methylene blue, this is a cofactor for the enzyme methemoglobin reductase, and this helps to convert methemoglobin into the normal hemoglobin. Carbon monoxide also causes shifting of the curve to the left, and it is a silent killer. When carbon monoxide binds to hemoglobin, the result is carboxyhemoglobin. Normally, 1% of hemoglobin is present in the form of carboxyhemoglobin. Of course, in smokers, the percentage of carboxyhemoglobin is greater than in normal, 5 to 10%. And symptoms begin to appear when the percentage of carboxyhemoglobin is around 25%, and the subject would die if 50% of the hemoglobin is in the form of carboxyhemoglobin. Carbon monoxide, the affinity of hemoglobin to bind carbon monoxide is 250 times greater than the affinity for oxygen. So now, whatever oxygen is left bound to hemoglobin, hemoglobin will not release it, will bind it very tightly. So here, this is the normal blood, where the percentage of carboxyhemoglobin is 0 or around 1%, and this is anemia. No problem with that. It's different from carbon monoxide poisoning, but the oxygen content is much less reduced in anemia, of course, depending on the level of the hemoglobin, and this is carbon monoxide poisoning. The oxygen content has decreased because the hemoglobin is now engaged with binding carbon monoxide, because its affinity for binding carbon monoxide is 250 times the affinity for binding oxygen. And whatever hemoglobin left binding oxygen, now it binds oxygen very tightly. So the curve, which is in solid black, is shifted to the left. Now we finish with the transport of oxygen, and now let's very briefly describe the transport of carbon dioxide. Approximately 10% of carbon dioxide is transported dissolved in the plasma. Remember, carbon dioxide is 20 times more soluble than oxygen. 30% of carbon dioxide is transported bound to hemoglobin, giving rise to carbaminohemoglobin. Other proteins in the plasma can also bind carbon dioxide. As more oxygen is bound to hemoglobin in the lungs, more carbon dioxide will be released. Again, this takes place at the level of the lung, and this is known as Holden effect. So this is the effect of oxygen binding to this is the effect of oxygen on carbon dioxide binding to hemoglobin. What's the meaning of this? So, as more oxygen is bound, less carbon dioxide binds to hemoglobin, and more carbon dioxide will be released. This is at the level of the lungs. What we have at the level of the tissues, now oxygen is released. And as more oxygen is released, more carbon dioxide will be bound. Again, this is Holden effect, and this takes place at the level of the tissues of the body. Most of the carbon dioxide, approximately 60%, is transported in the form of bicarbonate. So at the body tissues, carbon dioxide, which is produced by cellular metabolism, it diffuses into the interstitial fluid, then it diffuses into the blood, and it enters into the red blood cells. Inside the red blood cells, we have the enzyme carbonic anhydrase, and carbon dioxide gets hydrated. So carbon dioxide plus water, here we have the influence of the carbonic anhydrase, we have carbonic acid, then carbonic acid dissociates to hydrogen ions and bicarbonate ions. Accumulation of bicarbonate ions in the red blood cells causes them to diffuse to the plasma, and chloride ions enter in exchange for the bicarbonate ions, and this is known as the chloride shift phenomenon. At the lungs, the opposite happens. So now, at the lungs, what happens? Chloride ions get out and the bicarbonate ions get in. The bicarbonate ions bind to the hydrogen ions, resulting into carbonic acid. Then carbonic acid dissociates to carbon dioxide and water, and carbon dioxide is expired. Remember, the protons here, which result from the dissociation of carbonic acid at the level of the tissues, they bind to hemoglobin. At the level of the lungs, the bicarbonate ions which enter and the chloride ions which leave, now the bicarbonate ions, they take these hydrogen ions or the protons from hemoglobin. So this is a summary of what we have. So this is at the body, at the level of the body tissues. Carbon dioxide is produced by the cellular metabolism, diffuses to the intercellular or interstitial fluid, then it diffuses into the blood. Inside the red blood cells, carbon dioxide with water, carbonic anhydrase, carbonic acid, it dissociates to bicarbonate and protons or hydrogen ions. Hydrogen ions binds to hemoglobin. Bicarbonate diffuse out, chloride diffuses in. This is chloride shift phenomenon at the level of the tissues. At the level of the lungs, here we have now alveoli. We have again a chloride shift taking place at the level of the lungs, but in the opposite direction to the chloride shift which we have at the level of the body tissues. So chloride ions get in, get out, and bicarbonate ions get in. Bicarbonate ions take the protons from hemoglobin. So we have carbonic acid. Carbonic acid dissociates to water and carbon dioxide. Carbon dioxide diffuses to the alveoli, and the body gets rid of carbon dioxide during the process of expiration. So I finished with the carbon dioxide transport. And now let's describe the pulmonary blood flow in short. Remember, the right ventricle pumps deoxygenated blood into the pulmonary artery. Then we have this deoxygenated blood flows through the branches of the pulmonary artery, the pulmonary arterioles, then the pulmonary capillaries. So these pulmonary capillaries, they perfuse the alveoli. The alveoli are surrounded with the pulmonary capillaries. Then in the pulmonary capillaries, we have exchange of gases, as we mentioned in this lecture and in the previous lecture, and the blood which returns to the left atrium via the pulmonary veins is oxygenated blood. So all the cardiac output which is ejected by the left ventricle and goes through the tissues, it returns to the right side of the heart. Then the right ventricle ejects an equivalent cardiac output to the lungs, because the two circulations, the systemic circulation and the pulmonary circulation, are in series. So the lungs have a large quantity of blood. In fact, blood accounts for approximately half of the weight of the lung. And you all know from the anatomy that the heart is located about midway between the apex of the lung and the base of the lung. So in an individual who is standing upright, we can consider each lung to be 30 centimeter high water column from the base to the apex. This is because of the blood in the lung. Because of the effect of the gravity, the mean pressure in the pulmonary artery at the top of the lung, at the apex of the lung, is about 11 millimeters, less than the pulmonary arterial pressure in the middle of the lung. And the mean pulmonary arterial pressure at the base of the lung is about 100 millimeters greater than in the middle of the lung. So when someone is in the standing position, the pressure in the branches in the pulmonary artery at the apex of the lung is 11 millimeters of mercury less than in the middle of the lung. And at the base of the lung, the mean pulmonary arterial blood pressure is 11 millimeters higher than the mean pulmonary pressure in the middle of the lung. So this has a profound effect on the distribution of the pulmonary blood flow. So theoretically, the lung can be divided into 3 zones. Here we have 3 pressures interacting together, and these 3 pressures determine the pulmonary blood flow. These pressures are the BA is the alveolar pressure, PA small is the pulmonary arterial pressure, PV is the venous pressure. So this is the pulmonary arterial pressure, and this is the pulmonary venous pressure. Why do we mention the alveolar pressure here as a factor that determines pulmonary blood flow? Remember, the alveoli, they are filled with air, and the pulmonary capillaries surround the alveoli. So if the pressure in the alveoli is higher than the pressure in the pulmonary artery, so the pulmonary artery would be collapsed and no blood goes through the pulmonary capillaries. So theoretically, in zone 1, which is the upper zone, the alveolar pressure is greater than the pulmonary arterial pressure. Why? Because of the effect of gravity. We mentioned that the pulmonary arterial pressure is 11 millimeters of mercury, less than the pressure in the middle zone. And the pulmonary arterial pressure is higher than the pulmonary venous pressure. So as a result of this, we might expect that the pulmonary capillaries would be collapsed and there is no flow of the blood. However, normally this is not the case. This is not the case. Why? Because in zone 1, still the pulmonary arterial pressure under normal condition, it is still greater than the alveolar pressure. However, there is flow then. If the pulmonary arterial pressure is greater than the alveolar pressure, so the pulmonary capillaries will not be collapsed and there will be flow. Theoretically, we might think that there is no flow. However, in reality, still the pulmonary arterial pressure is greater than the alveolar pressure. So the pulmonary capillaries are not collapsed. If the pulmonary arterial pressure becomes too low, like what we have during hemorrhage, or if the alveolar pressure becomes too high, for example, during positive pressure breathing, now in this scenario, the zone 1 would exist and there will be no flow through zone 1. So physiologically, under normal physiological condition, there is no zone 1, if you like. Zone 2, now in zone 2, the pulmonary arterial pressure is greater than the pulmonary, the alveolar pressure, and the alveolar pressure is greater than the venous pressure. So blood flow is determined by the pressure gradient between the alveolar pressure and the arterial pressure. In zone 3, now in this scenario, the arterial pressure is higher than the venous pressure and the venous pressure is higher than the alveolar pressure. So blood flow is now determined by the pressure gradient between the arterial and venous. So zone 3 has got the highest flow. So, in the lung, in the upright position, we have an even or unequal distribution of the blood flow because of the effect of gravity. Zone 1 at the apex of the lung has the lowest blood flow, and zone 3 has the highest blood flow. Zone 3 is the base of the lung. So this is what we have here. So the base has got the highest blood flow, and the apex has got the lowest blood flow in the upright position. So gravity plays an important role in the regulation of the pulmonary blood flow. What are the other factors which regulate pulmonary blood flow? The partial pressure of oxygen in the alveolar air plays a very important role in determining pulmonary blood flow. As the partial pressure of oxygen in the alveolar air increases, pulmonary blood flow increases, because now the perfusion increases because it wants to perfuse better ventilated areas. On the other hand, as the partial pressure of oxygen in the alveolar air is decreased, pulmonary blood flow decreases because this regional hypoxia causes pulmonary vasoconstriction, because we do not want to perfuse poorly ventilated alveoli. So this is now a defense mechanism in order to direct blood to the better ventilated alveoli. And this defense mechanism is effective when there is only regional hypoxia. If there is generalized hypoxia, it is not effective. So this is what we have during regional hypoxia. Okay, here this is an alveolus with hypoxia with less oxygen in the alveolar air, so we have vasoconstriction. So here we have this normal alveolus, now it has got more blood. When there is generalized hypoxia, we have vasoconstriction throughout the pulmonary circulation. Other factors which regulate pulmonary blood flow include the nitric oxide, which is known as the endothelial-derived relaxing factor. This is a factor which is derived from the endothelial cells, and it causes relaxation of the smooth muscle cells in the wall of the pulmonary arterioles. So it causes pulmonary vasodilatation and it increases pulmonary blood flow. Prostacyclin or prostaglandin I2, it is also produced in the endothelial cells by the cyclooxygenase pathway, and it causes pulmonary vasodilatation, increasing pulmonary blood flow. On the other hand, thromboxane A2, this is produced in the macrophages and in the leukocytes in the endothelial cells in response to lung injury, and it causes vasoconstriction and it decreases pulmonary blood flow. Another thing which plays a role in the regulation of the pulmonary blood flow is the pulmonary vascular resistance. The pulmonary vascular resistance is dependent on the lung volume. So the lung volume itself determines the resistance, and the resistance determines the pulmonary blood flow. So the pulmonary vascular resistance is high at low lung volumes. Why? Because at low lung volumes, the increased intrapleural pressure compresses the pulmonary artery and vein. Similarly, at high lung volumes, the resistance is high, and in fact it is highest at high lung volumes, because overinflated alveoli would compress the pulmonary capillaries, and the resistance is lowest at the functional residual capacity. So we can see here on the x-axis the lung volumes, and on the y-axis the pulmonary vascular resistance. So at low lung volumes, the residual volume, it is high. At total lung capacity, which is the high lung volumes, it is highest, and it is lowest at the functional residual capacity. Another very important characteristic of the pulmonary vascular bed is its ability to handle large increases in the cardiac output without a dramatic increase in the pressure. Why? This is because the increase in the expected increase in the pressure, which is brought about by increase in the blood flow, is accompanied by a reduction in the resistance. So if the resistance is not decreased, we might expect that the increase in the cardiac output will increase the pressure. But this doesn't happen because the resistance is decreased. So the pulmonary vascular resistance decreases with increased cardiac output. And the mechanism that underlies the decrease in the pulmonary vascular resistance when the cardiac output is increased, in fact, lies in two mechanisms: the capillary recruitment and capillary distension. Capillary recruitment means that the closed capillaries open up. The closed capillaries where? Where do you have closed capillaries? Again, at the apex. We mentioned this. And we have capillary distension. So the pulmonary arterioles and the capillaries, they are highly compliant. يعني طوعية. لما يجي له كمية دم أكثر يحصل لهم طوعية ويحصل لهم distension تتسع. So now we have three beneficial effects of this. So an increase in the cardiac output from the right side of the heart will not increase the pulmonary pressure. What are the three beneficial effects of this? Now, this opposes the increase in blood flow velocity with increased flow rate. If the resistance has not decreased, the blood flow rate would have increased, and there will be no enough time for gas exchange. But this doesn't happen. The increases in pulmonary capillary surface area for more efficient gas exchange. Now the capillaries open and the capillaries dilate because more blood is coming. And as more blood comes, we need more efficient exchange of gases. And it is also protective in order to minimize the increase in the hydrostatic pressure. So it somehow prevents excess movement of fluid into the alveoli, so it keeps the alveoli dry. Now imagine the opposite scenario. Imagine that now there is an increased cardiac output from the right side of the heart, and the pulmonary vascular resistance has not decreased. There is no capillary recruitment. There is no capillary distension. So this would increase the pulmonary pressure. And the increase in the pulmonary pressure would result in movement of the fluid into the alveoli, resulting into alveolar edema. And this is a serious condition. So here we have, these are the normal pulmonary artery capillaries. This is pulmonary arteriole. This is recruitment. Now the collapsed capillaries at the apex of the lung are now recruited and open. And not only we have recruitment, but we also have distension. So in this figure, on the x-axis, this is the pulmonary arterial pressure, and on the y-axis, this is the pulmonary vascular resistance. And this is the cardiac output. Can you see here? As the cardiac output increases, we might expect an increase in the pulmonary arterial pressure. But the pulmonary arterial pressure does not increase much. It increases only very slightly. Why? Because with the increased cardiac output, the pulmonary vascular resistance is low. At normal cardiac output, this is the normal resistance, which is say 100% of the resistance. This is 100% of the resistance. At increased cardiac output, the resistance, the pulmonary vascular resistance, is 70% of the normal, and with decreased cardiac output, the pulmonary vascular resistance might double, become 200%, or even triple. It could be 300%,